Parkes Radio Telescope is a 64-meter telescope that has played a very important role in our history and is really freaking cool. Its first claim to fame was when it aided in the Apollo 11 mission by transmitting the primary TV signal. There's actually a movie called The Dish, which is an inaccurate portrayal of this event. Upon arriving to the Dish, John Sarkisian showed us around and gave us a lot of information on it, including their new program, Search for Extraterrestrial Intelligence, or SETI, where they are using the Dish to search for aliens.
Do it fast.
And that's about how it will go if they find it. We will all know as they will be too excited to contain themselves. The dish is held to the building by its weight. It is not bolted down or physically attached, which almost caused an issue during the Apollo 11 mission. It has also participated in the Galileo mission to study the Jupiter moons. But its primary mission as a radio telescope is more important. You may be asking, what's more important than looking cool and not finding aliens? Well, they detect pulsars. Lots and lots of pulsars. So what's a pulsar? Pulsar is a neutron star that has its magnetic poles misaligned with the rotational axis and emits energy in radio waves, which we can detect with radio telescopes like the Dish. Shown as a visual using visible light instead of radio waves. See how our pulsar has its magnetic poles? Here it's represented by flashlights. They're not lined up with his rotational axis. That is exactly what happens in space, and the camera represents a radio satellite on Earth, which is receiving the signal. Pulsars are extremely consistent, sending a signal at the exact same interval for our entire lives, but every once in a while, it skips a beat. Pulsars can spin very fast, as quick as 700 times a second. Kind of as fast as Barry Allen, except if the flash just ran in circles. And for unknown reasons, pulsars will shut off for a long period of time, as short as a few hours and as long as several years. This is our theory as to why pulsars stop. Dr. George Hobbs talked to us at CSIRO about pulsars and gave us all of this great information and more, like time slowing down due to massive objects, and showed us scientific data to prove it. To learn more, please proceed to your local recruiting study abroad office. Dr. Hobbs gave us a nice little fact about pulsars that gravitational wave scientists didn't want us to know. When gravitational waves were discovered, they thought it would be from colliding pulsars, but this was not the case. Dun, dun, dun! So then, what causes gravitational waves? What are gravitational waves? And how the hell do we know it exists? Gravitational waves are a ripple in the fabric of space-time. Kind of like this. And black holes are the cause of these. But wait, black holes? Then there would be gravitational waves everywhere, right? No, because a binary black hole system has to degrade in orbit enough to crash and then merge to send out a gravitational wave. Like so. Alright, so you know what they are and what causes them, but detecting them is tricky. To do this, there's a detector called LIGO, which uses a bunch of fancy equipment and lasers, like sharks with freaking laser beams on their heads, but without the sharks. So it's got these two arms that are each 4 kilometers long, and when a gravitational wave passes, the arms move, and the movement is detected by the difference in the recombination of the lasers, and poof, we have a result. Well, if both stations move and get the same reading, that is. So these two LIGO detectors have to move the arms at almost the same time. I said the same time. Thank you. It looks the same, but it's actually several nanoseconds apart, which allows us to see which direction they come from so we can locate the black holes in question. So now that you know what a gravitational wave is, let's talk about the black holes that cause them. A black hole is a remnant of a star that was at least 8 times larger than our sun. And it doesn't suck like magnitudes. No, really, they don't suck. The force of their gravity is the exact same as it was when it was a star, except now, instead of it being freaking gigantic, it's a small area with such a strong gravitational force that once light passes a certain point, called the Schwarzschild limit or event horizon, light cannot return. After that point, it's impossible to come back without going faster than the speed of light, which, isn't exactly easy. We observe a black hole by using the objects that orbit around it. These things will look like they're orbiting around something, but there won't be anything we see in the center of it all. The areas also tend to be very bright with a dark spot in the middle. That dark spot is, as you probably guessed, the black hole. These and dark matter, something we don't know much about other than there's a buttload of it, can bend light and distort the way we see space. This is something we call gravitational lensing. Have you ever thought, how the heck do these people know dark matter exists if we can't actually see it? Did the physicists just make this stuff up to balance their equations? Alright, picture this. From your knowledge of our solar system, which planet orbits fastest? Mercury, next to the sun, right? Which orbits slowest? Neptune, the furthest from the sun. Kepler's third law gives us an equation which helps us see this. Logic dictates that a similar pattern should be present for the whole galaxy. The galactic core should rotate much faster than its spiral arms, right? But something is wrong. The outer arms rotate faster than they should. Something is providing mass and gravity to our galaxy, to all galaxies, and it's completely invisible. This effect is due to gravitational lensing. The mass of the invisible dark matter causes light to bend and distort around it before being collected by the telescope. So dark matter and black holes cause gravitational lensing. Does anything else? Yeah, look at the sun. Okay, don't. Bad idea. Way too bright. But what if the sun wasn't so bright? Say, during a total solar eclipse? The light of the sun is blocked out, but you can now see the light of the stars bending around the sun due to its high gravity. These are just a few of the things that have expanded our education in astronomy while in Australia. Now it's time for the Kawakas! We ended this amazing 4-week experience in Wyoming with a total solar eclipse and an engagement.
Did you see the shadow yet?
Is that the shadow?
Where?
Here it comes.
Where is it? Wait, what are we looking
Coming from that way.
at? Oh my god.
That's so cool.
Ah!
Look it up.
Oh my god.
Yeah!
Oh my god.
Oh wow.
It just looks like a flashlight.
Oh yeah, you can almost see it.
A star!
Look, it's happening! It's happening!
Somebody turn on the lights, please!
Oh my gosh! Holy shit! Don't worry about it.
Oh my god.
Oh my god! Sunset all the way around.
Don't look at the sun!
That is so cool.
Don't look at the sun!
Oh my god! Oh, I love you, Gil.